Hello student, I am Assistant Professor Aparna Kedari. Today we are going to study stereochemistry and today's topic is compounds containing two chiral centers. So let's start with compounds containing two chiral centers. In this example, both carbons are chiral centered and they are adjacent. The first definition for mesocompounds and optically inactive compounds, even though these mesocompounds and optically inactive compounds, even though they possess more than one chiral center. Here there are more chiral center, but they are optically inactive and possesses plane of symmetry. Is called mesocompound. This mesocompound possesses the plane of symmetry. If we draw plane here, then it divides into two equal parts. Therefore, it has a plane of symmetry. And second, this chiral carbon has S configuration, and the second carbon has R configuration. Then consider this carbon rotate the plane of pluralized light to the left hand side by 30 degree. Simultaneously, this second carbon, which has R configuration, rotate the plane of plane polarized light to the right hand side by 30 degree. Therefore, this rotation get cancelled with each other, and therefore these mesocompounds are optically inactive due to the presence of plane of symmetry and internal compensation of these two chiral center. Therefore, mesocompounds are optically inactive compound. Next is the diastereomers. The definition for diastereomers: stereoisomers having two adjacent chiral centers and then that are not mirror images of each other are called diastereomers. Then properties of diastereomers. First, chemical properties. These diastereomers are not identical. They are different. Therefore, they react with same reagent but at different rate because the energy of activation required is different, and therefore their rates of reaction will be different. This is the chemical property of diastereomer. Second one is the physical property. Diastereomer have different physical properties like melting point, boiling point, solubility in given solvent, densities, refractive index. Because diastereomers distances between they have different arrangement of these atoms or groups of atoms. Therefore, the distance between various groups are different and hence intermolecular forces are different, and due to this they have different physical properties. Then next is the erythro and thioisomer. Erythroisomers means this is the Fischer projection, and in this Fischer projection, if two identical groups, that is here two identical groups are hydrogen atoms or atoms at two adjacent chiral centers are on the same side, then the isomer is called erythroisomer. And thioisomer, in Fischer projection, if two identical groups or atoms at two adjacent chiral centers are on the opposite side, then the isomer is called thioisomer. The next example is geometrical isomerism. The geometrical isomerism arises due to the restricted rotation about carbon-carbon double bond, and because when there is carbon-carbon single bond, then rotation is possible. It is free rotation, but when this rotation is restricted when carbon-carbon double bond is formed. Therefore, geometrical isomerism arises due to restricted rotation about carbon-carbon double bond. And there are two geometrical isomers which are shown by the compounds when containing double bond. First is cis isomer, that is Latin word. It is Latin word on same side. When similar groups or atoms are on the same side of double bond, it is called cis isomer. Then trans isomer means Latins mean across. When similar groups are on the opposite side of double bond, it is called trans isomer. Here example cis-2-butene and trans-2-butene. In cis-2-butene, the CH3 groups are on the same side of double bond and two hydrogens are on the same double bond. That is, if we consider only CH3 or hydrogen, they are on the same side of double bond, it is cis-2-butene. When they are on opposite side, then it is trans-2-butene. The next conditions for geometrical isomerism, first is the carbon-carbon double bond. Second one is the groups attached to olefinic carbon must be different. In this all examples, this carbon bears the same, this double bonded carbon bears or olefinic carbon bear same group. Therefore, these all three compounds do not show diageometrical isomerism. Then next is the designation E and Z configuration. When there are all different groups are present on the olefinic carbon, then designation E and Z, there is no cis and trans is used. For this type of compound, E and Z configuration is used. Z isomer means when both first priority groups are on the same side of double bond, the configuration is designated as Z isomer, and it is German word, that is zusammen, meaning together. Then E isomer when both first priority group, or if we in this case we consider second priority, this is also correct. When first priority group are on the opposite side of double bond, the configuration is designated as E isomer. Then here sequence rule is same sequence rule is used for RNS configuration. We are used in RNS configuration. Same sequence rule is used here. Suppose we consider the first doubly bonded carbon, then priority to this two atoms, chlorine gets first priority because the atomic number of chlorine is 1, and here fluorine atomic number is 9, therefore second priority to fluorine. Then consider this second carbon, to in this iodine is attached and bromine attached. Atomic number of iodine is greater, therefore first priority to iodine and second priority to bromine. When these two first priority groups are on the opposite side of double bond, therefore this configuration is E configuration. Then suppose these two, same example, these two first priority group are on the same side of double bond, then this configuration is Z configuration. Then next is the physical properties of geometrical isomers. Geometrical isomers have different physical properties such as melting point, boiling point, and refractive index, solubility, and density. They have all the physical property different. Here consider example cis to butene, trans to butene. Here mu is very small because there is flow of electrons to the one side, but this dipole caused by this carbon CH3 bond is cancelled by this carbon CH3, and therefore dipole moment is 0. Here boiling point is plus 4 degrees Celsius. Here boiling point is plus 1 degree Celsius. Then here melting point is minus 139 degrees Celsius. His melting point is 106 degrees Celsius. Then next is the chemical properties. The cis and trans not only differ in their physical properties, but they are also differ in the chemical properties. For example, the malic acid is heated. This is malic acid. These two COH group are on the same side, that is it is cis acid, and this fumaric acid is trans acid. And when malic acid is heated to 140 degrees Celsius, it readily cyclizes and forms malic acid, because here two COH group are on the same side and they are close to each other, therefore they easily condense or cyclizes and gives malic anhydride. But in case of fumaric acid, they are trans to each other, and therefore this cyclization is not possible. But when this trans isomer is heated at 300 degrees Celsius, then it get converted into malic acid. Then this two COH group becomes cis to each other, and then they undergo cyclization, gives malic anhydride. This is all about the chiral compounds containing two chiral center, meso compounds, and geometrical isomerism, E and Z designation, and the chemical and physical properties of geometrical isomerism.